Hey, 30-1s. Here we are in the second lesson of rational functions. What we're going to do here is we're going to analyze rational functions that aren't in that transformation form that we saw in the first lesson. What I want you to do, though, is grab your graphing calculator and not just watch and listen to me do this. I want you to do this. So what I'm going to get you to do is go grab your graphing calculator and draw this function, sketch it in there, and then see if you can answer the following questions. So hit pause and go do that, please. All right, you should have graphed that, and you should have seen something like that. So what we should be able to say is our vertical asymptotes at -2, our horizontal asymptotes at y=0. So this is going to help us find our domain and our range. So our domain is set of numbers x such that x can't equal -2. X is an element of the reals. Our range, same thing, just as y can't equal 0. Y is an element of the reals. Okay, our x-intercept, well, that's a fake. We don't have one, do we? Okay, our y-intercept, well, we certainly have a y-intercept. Now, I don't think I drew that thing too accurately. So to find a y-intercept, all you're going to do is let x equal 0. So I'm going to let x equal 0, and what do we get? We get 3/2. So our y-intercept is at 0, 3/2. Always write it as a coordinate pair, please. Okay, so I was pretty close when I drew that thing. Now our discontinuities, well, that's our asymptotes. So we have a horizontal asymptote. Again, I'm using an abbreviation just to save time. Don't use an abbreviation on a test, please. Horizontal asymptotes at x equals -2. And our vertical asymptote is at y=0. Hey, that wasn't too bad. Okay, what I want you to do now is to, same thing, grab your graphing calculator, and I want you to graph this one and fill in the chart. See you in a minute. All right. Well, I'm hoping you took the time to graph that. And when you did, I'm hoping you went, oh, maybe I graphed that wrong. I got a straight line. That's interesting. That doesn't look like the rationals that I've been seeing. Well, let's analyze this thing. First thing I want you to notice is that this function can be factored. So that's a difference of squares, x plus 3, x minus 3 over x minus 3. Okay, I see x minus 3 and x minus 3 divide out. And what am I left with? I'm left with x plus 3. Okay, well, hey, that's a nice linear graph from grade 10, isn't it? So y-intercept's at 3, slope is 1. So I can draw this thing. And it's going to look something like this. Okay, excellent. Okay, so there's the graph that my calculator gave me, or so I think. What I'm going to do here is I want to graph this thing as well in my graphing calculator, and there's a bit of a surprise in store for us. Okay, friends, I've got this thing graphed, x squared minus 9 over x minus 3. So I graph it, and there it is. And yeah, that's that straight line that I just drew as well. Well, what's the surprise? Well, here's the surprise. Let's go and substitute in a value. Now, I'm going to pick a very specific value here. I'm going to sub in when x is 3. Do you notice what we get? We get a y value says equal. There's nothing there. If we go to our table of values and I go up, or sorry, I go down to 3, what do you see? I see error. Wait a minute. What's going on here? Okay, let's go back and look at that function. All right, let's look at this function again. Now, what turns out that I drew wrong on purpose this time, I promise, is that, friends, there's actually a hole right here in that graph. There's a hole. When we went to go and find that value, our calculator said error. There's a hole. This is what's known as a point of discontinuity. So it's the point where we don't have something in our graph. There's a break in our graph. Okay, well, where did that come from? How did I know where to look? I went looking at 3. Well, look at your function, where the 2 factors divided out. So when 2 factors divide out, that's going to give us this point of discontinuity, or a POD for short. All right, let's answer some questions. Domain. Well, this graph doesn't have a vertical asymptote, but it has this point of discontinuity. So the set of numbers x such that x can't equal 3, comma, x is an element of the reals. All right, what about my range? Well, there's a hole in my graph. So there has to be a y value that our graph can't be. I don't know why I put 0. I just got excited there. Okay, what is it? We got to find that y value. So here's how you find that y value. Well, we know the point of discontinuity is at 3 comma something. Well, you know the x. So to find the y, you sub it into the simplified form right there. Well, 3 plus 3 is 6. Y can't equal 6. There it is. Now, our x-intercept. Our x-intercept is at negative 3 comma 0. Well, I want you to notice this. Look at that factor right there. Oh, the factor of my numerator gave me my x-intercept. Very interesting. Y-intercept. Well, again, y-intercept, I'm going to let x equal 0. I can tell it's at 3. There it is. So in this question, my friends, what we just found out is we have a point of discontinuity at 3 comma 6. So again, just an abbreviation, don't write it on a test. We have a point of discontinuity at 3 comma 6. So a point of discontinuity is new to you. You didn't see it in grade 11. A point of discontinuity occurs when we have a factor in the numerator and a factor in the denominator that are the same and divide out. That is your point of discontinuity. So this point here would be at negative a comma, whatever the y value would be. Okay, so there's something new for you from grade 11, a point of discontinuity. Okay, let's try another one. Let's put it all together here. So I know I said use your graphing calculator, but on this one, let's not. Let's see if we can figure this out without to start. So the first thing I'm always going to do on a rational function is factor. So this is a difference of squares, trinomial. Okay, I see 2 of my factors are going to divide out. And what are we left with? Well, we're left with x minus 1 over x plus 3. Okay, before we try to draw this, let's analyze the graph. What do we have? Well, a factor of our denominator is a vertical asymptote. So we have a vertical asymptote at x equals negative 3. A factor that divides out x plus 1 over x plus 1. That is our point of discontinuity. That's at negative 1 comma something. Well, I need you to know what that something is. So again, to find the y value, I'm going to sub it in to our simplified form right here. So I'll just do that just kind of down here. I'll erase it afterwards. So I sub that in. X is negative 1. What do we end up with? Well, I end up with negative 2 over 2 sounds like negative 1 to me. Okay, there's our POD. Now, the last thing I want you to be able to analyze from this, a factor of only my numerator is an x-intercept. Guess what? Your x-intercept's at 1 comma 0. Y-intercept, well, that's easy to find. Just look at our final form over here and let x equal 0. That's going to be negative a third. Just like that. Okay, see how much we can figure out just by factoring this function. Now, domain and range. Okay, let's put this all together then for domain and range. Well, domain is the set of numbers x such that, well, we've got a vertical asymptote at -3 and a POD at -1. So x can't equal -1, -3. This is an element of the reals. Range, well, for the range, what we need to look at is where's our horizontal asymptote. Okay, so I'm going to say for sure I've got this y value from the point of discontinuity, but this will have a horizontal asymptote. Okay, so how do we find that horizontal asymptote? That's the final question. So what we're going to do is we are now going to graph this. All right, let's graph this function. So I've got it in here. Let's hit graph. Let's analyze this thing. So I can see that we were right about our vertical asymptote and our horizontal asymptote. So that's good news. I can go to my table of values as well, and I can see, okay, look it, there's that point of discontinuity at -1, just like we said there would be. Okay, but what about the horizontal asymptote? That's the big question. Now, my friends, a horizontal asymptote is what happens as x goes to positive infinity and x goes to negative infinity. I'll say that again. Your horizontal asymptote is what happens as x goes to positive infinity and x goes to negative infinity. And we look at the y values. So there's several different ways for us to do this. One easy thing to do is to go to your table of values and simply change your x value to be a rather big number. So I'm going to go to my table, and there's my table. But I want big x values. So you notice where it says press plus for table set. So I'm going to hit plus, and it says delta table. So what do I want my x values to jump up by? Well, let's make x jump up by a big number. 1,000's a big number, right? If I had $1,000 in my pocket right now, I'd be really happy. So look at how this thing jumps up. Now look at your y values. Well, 501 over 499. Well, that's about 1. The next one, 499 over 501. Well, that's about 1. So what do we have here? As x goes to positive and negative infinity, these values are going to go towards 1. And to make that just a little bit more clear, all I've done is gone into my settings and changed it so instead of showing up as a fraction, it turns up as a decimal. So there we have it. There is one way to find our horizontal asymptote. So our horizontal asymptote was at +1. And so now we can draw this thing. Now, some of you might be saying, well, is there another way that I can find that horizontal asymptote? Yes, 100%. I'm going to show you how to do that algebraically in just a couple moments. Okay, there's that. Here's our vertical asymptote at -3. I think I've got, ooh, that's my y-intercept. Now I'm going to draw my graph. We've got a POD at -1, -1. And now I can draw this graph. Now, friends, I don't need you to know how to draw the graph completely without using your calculator. So I do expect you to pick up your calculator and to draw this thing. We don't fully know how to draw the arms of this graph until we learn some calculus. But there you go, my friends. There's that graph. It looks like it did on our graphing calculator. So one way to find the horizontal asymptote again is to let our horizontal asymptote was at y is equal to 1. To find that, all I did was let x be a really big number. And I figured out what the y was equal to. Okay, that's a numerical analysis approach to find the horizontal asymptote. Now, what we learned in the last class is the algebraic approach is to long divide this function. So there's two ways to do it. The shortcut way is to what I just did. The long, proper algebraic way is to do long division. There you go. Now, last question. Determine the equation of the following function in factored form. All right, so here we go. Let's go. Factored form. Well, I'm going to start with my vertical asymptote. It's at -4. So a vertical asymptote is a factor of the denominator. My POD, well, I see it right here. It's at positive 2. So my point of discontinuity is a factor of the numerator and the denominator. Now, the thing I find a lot of students miss their first little while is they forget the x-intercept. The x-intercept is a factor of the numerator. And then if we remember that, the last piece I need you to remember is that vertical stretch. I can't tell by looking at this thing if it's been vertically stretched. So if I do want to find that a value, what I'm going to have to do is I'm going to have to sub in a point. Now, I don't have a point nicely labeled for us here, but it sure as heck looks like -2, -1 is on that graph. So I'm always going to state what value I'm subbing in, and then I'm just going to simplify this down. So -1 is equal to a over -2 plus 1 over -2 plus 4. I'm not going to include these. Those are going to divide out anyway. And so I'm going to get -1a over 2. And so now what are we going to end up getting? We're going to end up with a is equal to 2. And there it is. So what's our full function then? Well, for full marks then, let's write this out. This is going to be f at x is equal to 2, x plus 1, x minus 2 over x plus 4, x minus 2. There it is. I don't feel the need to distribute those binomial factors. I'm happy. I can tell that you've done it right if that's on a test. Okay, so let's wrap this all up, friends. A rational function in factored form can be written as vertical stretch, x-intercept is a factor of only the numerator, a POD is a factor of both the numerator and the denominator, and a vertical asymptote is a factor of only the denominator. So a vertical asymptote is a factor of only the denominator. An x-intercept is a factor of only the numerator. A point of discontinuity is a factor of both the denominator and the numerator. Now, as the x values approach a point of discontinuity, there will be a hole in the graph. So what we did in the last couple examples was to find the coordinates of the y part of the coordinate. You're going to substitute that x value back into the simplified form. Okay. The thing that I see students forget quite often, don't forget your vertical stretch. Always assume it's been stretched. Now, talking a little bit about calculus, as the x values of a rational function approach a vertical asymptote, the y values will go either to positive or negative infinity. They will grow without bound. Okay, again, look at your table of values for that. Now, horizontal asymptotes, like I was saying, there's more than one way to find it. So the algebraic approach is to long divide like we did in the other lesson. A shortcut when I'm asked to only state it is to let x approach a big number. So that's where I changed my table of values. I usually just let x be 1,000, my friends. And whatever the y values are approaching, that's my horizontal asymptote. I need you to know that this is a shortcut. And if I ask you to determine, which is one of your directing words in 30-1, you need to know you have to show me work. Now, there is one other shortcut that I see a lot of times in resources. It works. It is the beginnings of calculus in a way, analyzing it. Okay, but as I've said here, don't try and pull this move in calculus. So here's how we analyze this. We compare the degree of the numerator and the denominator. So we've got 3 cases where the degree of the numerator is bigger than the degree of the denominator. So 2 is bigger than 1. Where numerator is smaller than denominator. So in this case, this is our most basic one. And where they're equal to each other. Okay, I'm going to start at the bottom and go up. Well, looking at this one here, where the degrees are equal to each other, what's going to happen is if you sub in really large numbers for x, essentially the numerator and denominator are going to grow at the same rate. The 1 is going to become almost meaningless. Like if you think about subbing in $1 million for X, well, $1 million bucks plus one more dollar, you don't care. You still got $1 million bucks. The plus 1 doesn't change much. So what's going to happen is the X's are going to grow at the same rate, and what we'll be left with is just 2/3. So what we do in this case is we divide the lead coefficients. In the case above, where the numerator is less than the denominator, well, this is our very most basic case. This is our original rational function. But picture what happens when you sub in a big number like 1 million in for X. Well, 1 divided by 1 million is basically 0. So it will always be at 0. Okay, so there's that one. That was easiest one. It's always at 0. And then the top one, friends, when the top is bigger than the bottom, if you sub in a big number in for X, the top's going to grow faster than the bottom. So this will grow without bound. We won't have a horizontal asymptote here. So I don't need to worry about this case in 30-1. In fact, what we get in calculus next semester is what's known as a slant or oblique asymptote. So really for us in 30-1, you're really only looking at these two cases. Again, it's a shortcut. If I ask you to algebraically determine, I want to see some division. Okay, amigos, I hope that was helpful. I will see you next time.